Hello, I'm Umnik. I will solve second division in the first round 897, and I will try to explain what I'm doing. Start with problem A. Have an array of lengths n. We want to find the permutation of the same length. The number of distinct numbers in element-wise difference array and permutation is maximized. If we sort the array and then take B as just I guess decreasing permutation I want, then the array of differences will be strictly sorted. I cannot sort array A, but I can rearrange the permutation so that it is in the same order. So that's what I want to do, I think. So I will sort the input array, but with remembering the original positions, and now I want to write the permutation in decreasing order, but on the positions that I remembered here. Problem B, binary string of length n. Number x is good. There exists binary string of length n with exactly x ones. So good is the number of ones, such that if each symbol is replaced, so we take bitwise XOR, then string s becomes a palindrome. Okay, so there are positions that are symmetric with respect to the middle of the string that we will compare when we're checking if something is palindrome or not. And let's look at those characters. If they're equal now, then we don't want to change that. So we want to have to XOR either both of them with 0 or both of them with 1. So we can have either no ones or 2 ones for such pair. For a position where the characters are different, we want to make them equal, so we need to XOR exactly one of them with 1. So for those pairs, we must have exactly one character 1. So for every pair, either it just gives us +1, or we can choose plus 0 or plus 2, so we count how many of pairs of both types we have. And then we have the number of ones we must use, and then we can add some number of twos. But there is also, if the string is of odd length, there is a character in the middle that we don't care about, so we can just put it either 0 or 1 here. And if we don't have such a character, then we will just have from minimum there will be all good numbers will be those arithmetic progression with sequence with step 2, and if we do have the middle character, then we can also add 1 for free, so we will just have a segment of good numbers. Both cases are not that hard to do, so let's just implement that. So now I'm iterating over the pairs. If the characters are equal, then I will say that I have one more pair of that type. Otherwise I have one more pair of this type. And so if n is even, so all the characters are in pairs, then a once is good, a plus 2, a plus 4, and so on, while until I reach a plus 2 times b. And here just everything from a to a plus 2 times b plus 1 is good. I want to prepare the string I will print. Okay, something is very wrong. Problem C is an interactive problem. There is a set of n distinct integers. They are non-negative but can be 0 and can be very big. Let's decide to play a game with the set against Bob. The rules of the game are as follows. Player takes turns. In one move, Alice adds one number to the set, and that must be a new number. So it wasn't present in the set before. At the time of insertion, maybe before it was, I don't know. In the next move, Bob removes one number from the set. number y must be strictly smaller than the last number added by Alice. The game ends when Bob cannot make a move or after 2 times n plus 1 moves. The result of the game is max. Alice aims to maximize the result, Bob aims to minimize the result. Kind of hard to understand what's going on. Let R be the result when both players play optimally. In this problem you play as Alice. Task is to implement strategy for Alice that the result is always at least R. Okay. Do not attempt to hack this problem. Cool. Okay, so we have numbers. Alice insert new number. After that, Bob removes a smaller number. If there is no smaller number, then Bob doesn't remove it. Can't Alice just like guarantee n plus 1? Like 2 n plus 1 moves, so Alice's move, Alice will make at most n plus 1 moves, and we can try to have and like after each of Alice's moves there are n plus 1 numbers in the set, and then Bob removes one if he can, so there will be n numbers in the set, then n plus 1 n, n plus 1 n, and always Alice's move is the last one, right? Because either Bob cannot make a move, so Alice just did make a move, or like it is just explicitly given that Alice will be the last move. So in the end of the game there are n plus 1 numbers in the set. So the best possible result Alice can achieve is the number n plus 1. If the set is just 0, 1, 2 and so on up to n, then all the numbers from 0 to n are excluded. So the minimum excluded is n plus 1. And I think Alice can just achieve that. Why not? Like here are numbers. Some of them we already have. Some we don't have. Let's say that we let's say that we have n minus 1 but we don't have n. Then in the first move Alice will insert n. So insert n. After that it is in the set, but then like Bob must remove numbers that are smaller. He will remove sums. remove 3. Then we have n-1, insert the next one. No, that's bad, right? If we didn't have any numbers from 0 to n in the beginning, then after we insert n, Bob just don't have any moves. But Bob always removes the number that is smaller than the one we inserted. So basically from some starting position, we can see a pair of moves, like when Alice inserts something new but then Bob removes it, like Alice inserts this number but Bob removes this number. We can imagine that we move this number to the right, we increased it. And so those moves will be some increases, and then Alice will make the last move. But then it kind of feels like Alice cannot do anything better than so take the smallest number that is not present initially in the set and insert it, and then the result will be the second minimum excluded number, this one. And after each of the Bob's moves, we can maintain that so that the result is here. We fill this gap, then Bob removes something, then we fill it back, then Bob removes something, then we fill that, and so on. And yeah, since we cannot fill more than two gaps, more than one gap, I mean. So the second of the existing gaps is the upper limit on the answer. Okay, yeah, and we can achieve it. So yeah, the strategy is to find max, basically, then insert it, and then while Bob removes something, we insert it back, and just wait until Bob is tired. Okay. So in the beginning, read n numbers and calculate their max. insert this number, and then just while Bob is willing to play, read his next move. If the game ended, well, just end. I mean, I can like assert that it is -1. Shouldn't make invalid queries. And if it is -1, then just stop playing this game. Otherwise, we want to insert that number back. Problem D. Have an array of lengths n, initially all elements are zeros, to make into another array B of lengths n. Only the following operation can be used, 0 or several times. Choose array of lengths k, all else are distinct. Change each element what to L. So like we choose some k indices in cyclic order, and then element that is on position this index we assign like the next index, the value of index itself. Whether it is possible to get array B using only these operations, and we don't need to print the actual thing, just whether it is possible. Okay, the operation sounds super weird. 1 second, but that's like input output, right? Okay. K is given. Okay. So we can only get elements like from 1 to n, and all the given elements are from 1 to n, but we start with zeros, so we need to apply the operation for every index at least once. Okay, and I guess it is like working backwards kind of thing, right? Look, assume that we applied some operation. So we have chosen some array, then on position, like on this position we will have L2, on this position we will have L3, and so on. So kind of if we imagine it as like from every position there is an edge to the element on this position, then this thing kind of takes k vertices in this graph and draws a cycle on them. Right? Like we basically say that from every vertex there will be like exactly one edge, or like we start with all the edges like pointing to 0, like not existing, whatever. But when we apply the operation, we just like draw the cycle like this. Okay, so assume we did that and we got array B in the end. There must be some last operation, right? There was some operation that we applied last. So in this graph, there must be a cycle of length k. If there is no such cycle, then it is impossible. Like there can't be any last operation, so there can't be any sequence of operations, obviously. But what if there is such a cycle? And well, generally we are given like some functional graph, and so like it has a cycle of size exactly k, but it can have some other things. There can be some other cycles, shorter cycles, longer cycles. Okay, so shorter cycles kind of sounds bad. I guess longer cycles too. Like if I want to apply the operation on some position, then I must also take the next and the next and so on. Okay, so the cycle, if I have a cycle of length that is not exactly k, that's bad, because I cannot start anywhere. But if all cycles are of length k, then like I can apply the operation to the cycle like kind of last, but we can imagine it by like undoing the operation. So there will be the last operation that like makes this cycle, and before that numbers could be anything. So can we fix this edge now? Well, yes, we can start with this vertex, like go here, and then just like we don't have outgoing edge right now because we already kind of fixed it, so it could be anything right now. So we can just look, and we have at least k vertices with like no outgoing edges, so we can draw like using k minus 1 of them, and then from here draw like this edge back, and that will give us the edge we want. So we need to start in the cycle, and the cycle must be of length k, but then we can just go back and fix all the edges that are not on cycles, except in the case where k is equal to 1. When k is 1, we must have just n cycles of like n self loops, because we can't make anything else. If k is equal to 1, then all our operations are just like some number, and like on this position put the same number that is this position. so we can't do anything else. So the solution is to okay, if k is equal to 1, we just check if it's like 1, 2, 3, and so on, n. Otherwise, we check that all the cycles in this functional graph are of length exactly k. If yes, then the answer is yes. If no, then no. Okay, so now the main part of the solution, analyze this given functional graph. So I marked everything that is not on the cycle with -1s, and now I just want to find the cycles and check that their length is exactly k. Problem E has subtasks. Interactive problem. The difference is the limit on the number of queries. Okay, so in easy version we have 100 queries, and in the hard version 57. Okay. There is a positive integer k. Let's play a game. There is an array of n integers. We want to find XOR of all the elements in this array. You can make queries of the following type. Ask some index and we will receive XOR from that index of subsegment of length k from that index. We know k. Okay. Also, after that query, the subarray will be reversed. Okay, but that doesn't change the XOR. Okay. N and k are even. And n lies between k and k squared. And k squared is at most 50 squared. The interactor is not adaptive, but I guess that shouldn't matter much. Okay, 157. Okay. So like 50 is probably like what this 50 is, and 7 is maybe like logarithm of that 50 or something. Like if we have an array, if the length of the array is divisible by k, then it's great. We can just split it into blocks of size k, ask about each block, XOR all those values, and we are done. And for that we will spend like n divided by k queries, but that is at most k, and k is at most 50, so great. But we have like this smaller part. Do we know n? Well, I guess we must know n, right? Otherwise we can make undefined queries. Yep, we are given n and k in the beginning. So I guess I want to somehow use the fact that blocks are rotated after queries. Maybe profitable to look at it as like prefix source, but I don't really see how yet. So what happens if I make a query and then make a query shifted right by 1? So we had some elements. Reverse this and reverse the result. -1 k and then just a normal order. So I took two elements and shifted them in front. 2 and k-1. I guess like this thing, like if this distance is d, then it would probably be like 2d here and k-d here. The interactivity probably doesn't matter. Like, I can't really extract any kind of information from the answers to queries. So like, I just need to construct a strategy of like those reversals so that I can just XOR some answers to some queries to get the result, to get the answer to the whole problem. I want every element to like affect XOR, so it should be counted odd number of times. And like some queries I can include in the answer, some queries I don't include in the answer. So like basically I can just imagine that I can reverse the segment without like counting it in the answer, and reverse the segment and XOR the answer with the result of that query. But what if I shift by D once more? Isn't that exactly what I want? So, like, let's say that I want to calculate the XOR on segment of length k plus 2d, where d is something that is smaller than k. Then what I will do is I will take 3 suffixes of length d each and the prefix of length k minus d, and then I will ask this k, which will reverse it, and so I will get this d and k minus d both reversed, but it doesn't matter for me. Then this segment, again I move this to the left, and then ask this segment. After that, every segment of length d was asked once, and the segment of length k minus d was asked 3 times. So all of that is odd, and so I just XOR them, that's the answer. And to solve the original problem, I will cut k until like n is between k and 2k, and then I know that n minus k is even because both of them are even, and I will take d as n minus k divided by 2, do this, and I will be done in like n divided by k plus 2 queries. Isn't that like much better than what is asked from me? What's the catch? Reversed. Well, no, I think that just works. East. Okay, I don't get what happened, but I think that's the solution. Okay, let's use 0 indexation and query will add 1. well, okay, it's either run cancer 1 or it just works. Okay, that was super weird. Problem F. There is a tree with n vertices rooted at 1. N is up to a million. That's a lot. PG is a multiset of subtrees of all vertices. Okay. To find a tree G prime of the same size, again rooted at 1, such that the number of subtrees so we are given a rooted tree. We want to construct a rooted tree of the same size, such that for the there as little as possible subtrees that are isomorphic to some subtree of the given tree. Okay, I think I understand the problem. Interesting. Bamboo must be a nice candidate for the answer, right? Every subtree is a bamboo, so we will have isomorphic subtrees in the given tree, like only for the bamboo subtrees. So the number of isomorphic subtrees will be like maximum size of bamboo subtree in the given tree, and those must be relatively rare. So like bamboo is bad if there is a big bamboo subtree. Oh, but I guess let's draw the smallest rooted subtree that is rooted tree that is not isomorphic to any rooted subtree in the given tree. Then the answer is just like add bamboo of necessary size to that, because all of those vertices, like all of their subtrees, are not isomorphic to anything, because like this would be isomorphic to something then. So we are actually asked to find the smallest rooted tree that is not isomorphic to any rooted subtree. But that should be doable by just like iterating through all of them. If we will have all the possible rooted trees sorted by size, we just iterate over them and find the first one that doesn't appear. I mean, that is certainly correct. Now I just need to understand how to generate them fast. I need kind of a lot of them. I don't know how many exactly, but like if let's say there are if there are 100,000 of different rooted trees of size 10, that will be enough already, because like all those subtrees of size 10, they must be non-intersecting, because if they are intersecting, then one lies inside another and they cannot have the same size then. So our given tree of size n can have only n divided by d rooted subtrees of size d. So like I need to generate some not very big number of them. Can I do it like in any reasonable way I want? I think so. So like the rooted tree is identified by like there is a root and it has sons that are also rooted trees. So we want to encode it as a multi-set of sons, so like sorted set of sons. If I will just generate all the trees of size 1, then of size 2, of size 3, and so on, like how to generate all the trees of size n if I already have generated all the trees of smaller sizes? Well, I want to choose the largest sun, then the second largest sun among the generated, so that the sum of sizes is like n minus 1, because I have the root. And since there is always an option to just add leaves, then I will there won't be any branches in the brute force that will not lead to new trees, and so I stop once I have enough trees to make sure that one given tree of size up to 1,000,000 cannot have all of those as smaller subtrees. Then I will read the tree, search which ones I do have, and find the first ones that I don't have. Kind of like this. Okay, so what I want to do is I want to write brute force that will try to construct all the sorted in non-increasing order vectors, so that the sum of the corresponding sizes is exactly s minus 1. Okay, so now we can check if, like, on OEs these numbers actually give the number of rooted trees. Number of unlabeled rooted trees. So it seems that my brute force is correct. It is surely fast enough, and we can see that with 15 vertices it's already impossible to contain all of them in one tree of size at most a million. So now I will read the input, find so I want to analyze like all the subtrees of size at most 15, mark the ones that I do have, then find the first ones that I don't have, and then I need to accurately print it as the answer. So I find what is the ID of each sum. If some of them are minus ones, then means that they're too big, I haven't generated them, and I don't care about them, therefore. find the first tree that I don't have, and then I need to print it. So I can find the size of that tree. So now I know that subtree has size S. We can assert that it is not bigger than n. I guess that won't be true for like super small values of n, if I guess n up to 2. So yeah, n equal to 2, I guess I need to solve separately. Because like it's the only case where in one tree we have all the subtrees of size up to n. For 3 there are already like 2 different subtrees, so at least one of them is not present. So I need to have a bamboo up to this small tree of size S, and then some recursive functions that will actually print all the edges of the tree of size S, but I need to like numerate the vertices correctly. So like we'll start with like, so print tree basically says like print the tree with this vertex number v as a root, and you should use like consecutive indices for vertices, and I will go through all the suns for every sun, like find its size and give that many vertices to it, and draw the edge from the root to the sun. I need to actually store the things that I construct. mean, it's not very interesting to look on samples. It should work. This will be slow probably, because like on every test they need to generate those 100,000 and something trees. So that's not super slow, but it takes some time, and it takes some time even on the like very small tests. And yes, there are a lot of tests, so but well, I'm sure that it's correct. So the problems. Problem F is kind of cute. Like the statement is very interesting. It seems like very unique problem. And problem D is also like in the same vein that it seems very like not like other problems. But I can't say that I like to solve any of the problems. Problem E is like super weird. Like if you have two versions of the problem and in the like okay 100 queries is like reasonable thing to say. 57, like if it is not optimal, then why? Why 57? What is 7? And like oh, maybe it's like number of the school in which they stay. Like they are Russian school children, right? Okay, they all use some weird things instead of actual school. Still running on pretests. But yeah, like my solution uses like 51 operation, and again, like I understand that the problem needs to be interactive, but it is not actually an interactive problem. Like you do not use responses in any way. Just like take sort of all of them and print as answer. You just need to construct like how to use reverses, but it's not an interactive problem. Yeah, yes. I don't like the problems in terms of like how they're solved. I like problems D and F as like they have nice statements. They are unique in a sense. And well, D and F are both okay problems, and they have very nice statement. So that's a win in terms of problem setting. You want to have either like very natural or unique statement, and even if the problem itself like boils down to some standard things, that's not bad. Like, still, like, you give people the opportunity to solve a cool sounding problem, or you want to have like a very cool solution that is very non-standard. Preferably both. And D&F surely have like nice statement, nice model, and the solution is fine. And all others, well, I guess problem C is kind of okay, but again, I don't see why it should be interactive. Does the problem really changes from being interactive? Couldn't they just ask for I don't know for what. I guess like asking for just the result of the game will be like, oh yeah, print second max, and this might be guessable if you like even if you don't understand the strategy that leads to result being second max, you can still guess. So maybe that's the reason. But again, the problem is not that interactive. I don't know. It's an okay contest. But I can't say that I really liked any problem. Yay, pretests passed. Thanks for watching. Bye.